Our new unit that we start today is called magnetism. Before we really get into magnetism, I have to define one term for you. It's called the domain, a magnetic domain. It is a region, a tiny little region inside a ferromagnetic material. A ferromagnetic material is a material that can become magnetized. Doesn't mean that it is magnetized, but it can become magnetized. You ever seen the term ferro before? Like that prefix ferro? Where have you seen that? Yeah, iron, right? It's the chemical symbol for iron, Fe, ferrous. Iron oxide used to be called ferrous oxide. Right? Iron is a pretty common example of a ferromagnetic material, a material that can become magnetized. So is nickel. So is cobalt. I'll put steel down as well, although that's not an element, right? That's an alloy, but it's an alloy of iron and some other things. It's a pretty common ferromagnetic material as well. Probably the most common one, actually, because it's such a commonly occurring material. So we got a tiny little region inside a ferromagnetic material, inside a material that can become magnetized, that we represent by arrows. So we're not suggesting here that for a second that if we look at a ferromagnetic material under a microscope, we're going to see arrows. Okay, we're simply representing these domains, these tiny little regions with patterns of electron spins and so on with arrows. Now, I'm going to draw a picture of a ferromagnetic material here. Again, this is not the picture that you would see literally if you looked in a microscope, because this picture has the arrows representing these domains pointing right now in pretty much random directions, it looks like. This ferromagnetic material right now has the ability to become magnetized or the potential to become magnetized, but it's not a magnet right now. When the domains point in random directions, which they normally do, then we've got a non-magnetized ferromagnetic material. It's just a regular piece of steel or a regular piece of iron. So how do we make it magnetized? Well, we try to align the domains. We try to start making the domains point in the same direction. So how do we do that? Think back to elementary school. I know you guys at some point, I can't remember what grade it was, did a unit on magnetism. You probably did a couple little activities on magnetism as well. You guys remember how you magnetized a nail to pick up thumbtacks? There's a couple ways you can do it. What's one way, Philip? Yeah, bring another magnet nearby. If I take another magnet, a permanent magnet with domains already aligned, with a north pole and a south pole already there, a permanent magnet, and I bring it nearby, then the effect that that has is to temporarily align the domains in this non-magnet. So this is my before picture. This is what it looks like before. When I put the permanent magnet nearby, then I'm going to get the same ferromagnetic material with the same domains, except now they're more or less pointing in the same direction. This is a magnet now. So we've taken this magnet, bring it nearby, and we temporarily align the domains in that magnet. Kind of like if we were to bring a charged object nearby a neutral object, we temporarily cause a separation of charge. Bring that object away from what we're trying to charge, and of course the charges go back to more or less the way they were. Happens here too. The domains more or less go back to being scrambled, although not right away. Okay, it's not going to be instant. Okay, if you magnetize a steel nail or a piece of iron or cobalt or something like that, make it a temporary magnet, and you bring the magnet that magnetized it away, it's going to still maintain a bit of a magnetic effect for a little while. Okay, it's not going to be an instant disappearing of it, but they are going to go back, the domains are going to go back to the way they were pointing before at some point. That's why we call it a temporary magnet. Now, this magnet, this temporary magnet that we just made has got to have a polarity. That polarity is going to be south pole down here and north pole up here. The domains will point from south to north. That's arbitrary, right? We define the direction of the domains because we are representing what's happening inside here by these arrows. So really the arrows could be defined as being pointing in the other direction, but they're not. It's arbitrary, but it doesn't matter. Okay, they're still defined as being pointing from the South Pole to the North Pole. What do you think would happen if you cut that magnet in half? Either the permanent magnet or the one that we just made. Yeah. Yeah, you'd have two separate magnets, both with a south pole and a north pole. You can't have, this is one of the differences between electricity and magnetism. You can have a positive charge. You can have a negative charge by themselves. Of course, you can have positive and negative together as well. You can't have just a north pole or just a south pole. If you cut this in half, then you're going to get a south and a north and a south and a north. You always have to have those two poles. Our laws of magnetism, you're going to find our first real similarity between magnetism and electricity here. You guys remember the laws of electricity that we learned in our last unit? You did pretty well on that test, so I think you remember. Opposites attract, opposite charges attract. What's the next one? Like charges repel each other. We're going to say like poles repel each other as well. Just like positive repels positive and negative repels negative. North repels north and south repels south. Doesn't mean that north is positive. Boy, it sure behaves like positive sometimes. North repels north, just like positive repels positive. Unlike poles attract, north attracts south, just like positive attracts negative. You guys remember the third one? The third one's the toughest one. Yeah, Caitlin? Yeah, or negative, yeah. Charged objects, so positive or negative objects, attract neutral objects. And that happens because of a temporary separation of charge. Remember that? Charged objects attract neutral objects because of a temporary separation of charge. Let's see if you can figure out the third one from cartoon. So we got a magnet here nearby a nail, a steel nail. The magnet is attracting the nail. Of course the magnet's attracting the nail. Why? Because we've got a magnet and we've got what is the nail? Not neutral, a ferromagnetic, a non-magnetized ferromagnetic material. So we're not going to say that charged objects attract neutral objects this time. Rather, we're going to say that north and south poles or magnets attract non-magnetized ferromagnetic materials. This is important, by the way, okay, because you bring a magnet nearby a piece of paper, what happens? Nothing. Magnets don't attract non-magnets. Magnets attract non-magnetized ferromagnetic materials. And the reason that you need to have ferromagnetic material is because in order to attract it, you need to temporarily align the domains in the non-magnetized material. So if you've got a material here that is ferromagnetic but non-magnetized, domains pointing in random directions, and you bring another object nearby that is magnetized, let's say with a south pole and a north pole, and the domains pointing like this, then what you're going to cause is these domains to temporarily align like this, giving this a temporary south pole and a temporary north pole, meaning that these two poles are going to attract. So this was non-magnetized. We temporarily magnetize it by aligning the domains, and that's going to cause the south pole of the original magnet to attract this, what previously was non-magnetized. Yeah, question? This one here? Yeah? Yes. So let's do that right now, actually. Okay, let's say that we've got this non-magnetized ferromagnetic material with the domains pointing more or less in random directions. And we put this other magnet that we had, instead of putting it to the right, we put it to the left. with a north pole and a south pole, and the domains pointing, of course, from south to north. What's going to happen here? Well, we're going to cause the domains to point in still the same direction, temporarily align those domains pointing like this, which means that this becomes a south, this becomes a north, and of course, they're still going to attract each other. Does that make sense? Yep. Yeah, go ahead. Oh, that one. Let's try another one here then. Dial in, that's a good question. So let's say we've got our non-magnetized ferromagnetic material again with the domains pointing in random directions, and then we bring our magnet nearby, but this time has a north pole on the left side and a south pole on this side. We're going to have our domains pointing from south to north inside this magnet, which is going to cause these domains to temporarily align in this direction now, making this end south and this end north, and once again attracting. So non-magnetized ferromagnetic material, any way you look at it, is going to be attracted to this magnet because of this temporary alignment of the domains that occurs as a result of bringing it nearby. Now, there is another way to magnetize it as well. There is. Yeah? Yeah, you don't want to run electricity through it, but if you take a wire and wrap it around or run electricity nearby it, electricity, you're going to learn a lot more about this tomorrow, but electricity can generate a magnetic field. And if you've got the wires set up properly, then you can cause one wire to kind of, maybe the term I should use is interfere almost, like to cause constructive, a building up of a magnetic effect in this non-magnetized ferromagnetic material. We'll talk more about that tomorrow, okay? Don't worry about that right now. You bring a magnet nearby, it causes a temporary alignment of domains, it causes it to become a temporary magnet, and therefore it's going to attract, right? Okay, let's talk about magnetic fields now. We talked about electric fields a lot in our last unit. We defined an electric field as a region, who's got this? A region in which, well, an electric field would be a region in which an electric force could be experienced by a charge. A magnetic field would be a region in which a magnetic field could be experienced by a ferromagnetic material, right? By a magnet or by a ferromagnetic material. So again, I asked you before we started this to always keep in the back of your mind that we're dealing with magnetism here, not electricity. You start seeing a definition like this, and all of a sudden it seems like we're talking about what we talked about in the last unit. It's real similar in a lot of ways, including this, but it's not the same thing. Now, of course, electric fields surround electric charges, right? Magnetic fields surround magnets. Magnetic fields surround magnets. Now, they also surround, as Philip kind of alluded to a minute ago, they also surround electric currents or moving electric charges, but we're not going to worry about that right now. We'll talk more about that tomorrow. All right, it looks like everyone has completed their activity here now, mapping out the magnetic field that surrounds their magnets. What I want to do is draw what you should have seen, and then we're going to do a little kindergarten activity and connect some dots. Except it's easier than kindergarten because you don't even have to go like 1, 2, 3, 4, 5 in order. It's just connect things that look like they should form a pattern here. So let's look at what we should have got here. You should have seen something like this, a little arrow pointing to the left, away from the North Pole, a little arrow pointing to the left, pointing toward the South Pole. Maybe one here, maybe one here. Yours don't have to be exactly like this. In fact, they're probably not going to be exactly like this, right? But they should be more or less, at least, like this. As I was walking around, it looked like most groups had diagrams that looked more or less like this. Now let's join the dots together here, or connect the arrows together. Should look something like this when I do that. Notice these field lines are forming loops from north to south outside of the magnet. And notice as well that, I don't know if you caught this or not, but if I drew a positive charge here and a negative charge here, and I want to draw the electric field that surrounded these. The electric field would look exactly like the magnetic field that surrounds these magnets. We're talking about two different fields, magnetic field versus electric field, but the shape of those fields is exactly the same. Now notice I've left out the electric field between the positive and the negative charge. Okay, we know that that would go this way. The magnetic field inside this magnet actually points the other way, because really what that magnetic field inside the magnet is just the domains pointing from south to north. So why the difference there between the north and the south versus the positive and the negative? Well, fundamentally, it comes down to this is not inside electric charges. This is inside magnets. So the magnetic field outside of magnets will be from north to south, but the magnetic field inside magnets will be from south to north. Now, it's not very often that you're going to have to deal with the magnetic field inside the magnets. Okay, it's almost always, 90% of the time at least, we're dealing with the magnetic field outside. But inside the magnet, it goes from south to north, as opposed to from north to south. Let's draw the next one here. Here we've got all kinds of stars all over the place. We've got probably an arrow pointing this way. Something like this. Okay, again, not exactly like this necessarily, but should look kind of more or less like this at least. We start connecting the dots together and maybe it starts looking like this. Once again, with the magnetic fields pointing away from the north toward the south. I'm going to draw those charges again and draw the connection between the electric and the magnetic field. If we have a positive charge and a negative charge and a positive charge and a negative charge, the electric field between those or surrounding those would look something like this. Look closely at it, it should look exactly the same as the magnetic field that surrounds these bar magnets. Again, it's a different field, but the shape of that field is going to be exactly the same. What do you notice about the magnetic field in between the north and the south here? The magnetic field leaving the North Pole, the magnetic field going into the North Pole, sorry, the South Pole, they join up with each other. And what do we know happens if field lines join up, at least with electric fields? We get a force of attraction, right? Well, should these attract each other? Of course they should. We got a North Pole and a South Pole. And we learned a little while ago that opposite poles attract each other. North attracts south. So of course, we should predict that the field lines are going to join up because we know ahead of time that they're going to attract each other. Let's look at the next picture here. Here we got north against north. What would you predict for the field lines here? Clearly, these are going to repel each other, so the field lines are not going to join up, right? What are the field lines going to look like? Let's start drawing our little arrows here. Should look something like this. Approximately, at least like this. We start connecting the dots here and it starts looking like this. We could draw more field lines in here as well. It would look something like this. What do we see in the middle there, though? They don't join up, and they don't join up because north repels north. And when field lines don't join up, then we know we have a force of repulsion. Notice it's still leaving the north, going towards the south there. I could draw the charges down here as well, just like I did in the last two diagrams. And you'd find that the electric field surrounding it would have to be a negative, a positive, in a negative would look exactly the same as the magnetic field that we just drew. We've drawn these fields, and clearly, as we drew these fields with arrows on them, clearly we know that we have vector fields here, right? Magnetic fields, just like electric fields, just like gravitational fields, are vector fields. They have a direction associated with them. We can define that direction in two ways, just like we could define the direction of the electric field in two ways. If you remember from our last unit, and you better remember because you guys did really well on this test, the electric field direction is the direction of the force on a positively charged particle in that field. The direction of the magnetic field would be the direction of the force on a compass needle when placed in that field, or simply which way the compass needle points when placed in the field, specifically the north end of the compass. The compass needle has a north pole and a south pole, just like any other magnet does. The red tip of the compass needle, which is typically what we look at, is the north pole of the compass needle. We want to see which way it points. It points in the direction of the magnetic field. Now, we also say it points from north to south, just like the electric field also points from positive to negative. That is, from north to south outside of the magnet, it would point inside of the magnet, it would point from south to north. Although we don't worry about that too much because we don't usually look for the magnetic field inside the magnet. It's almost always outside of the magnet. This shows us, this table that we see on the board right now shows us the relative strength of various magnetic fields, starting with the magnetic field surrounding the Earth, which on average is about 10 to the minus 5 Tesla. The unit for magnetic field is a capital T or Tesla. The symbol, by the way, for magnetic field is a capital B with the arrow over it because we know it's a vector field. The unit is the Tesla. And the magnetic field strength surrounding the Earth is on average about 10 to the minus 5 Tesla. It varies by location. In some places it's stronger, in some places it's weaker. And in fact, it changes over time. Scientists have noticed actually over the last number of decades, the Earth's magnetic field has actually decreased in strength by about 10% or so. Like, that's significant. In fact, some scientists actually believe right now we're in the process of a magnetic field reversal. It's happened. Geological records show that about every 250,000 years, on average, the Earth's magnetic field will just reverse. And it happens not over a period of tens of thousands of years, but it happens over a period of decades, like literally over a period of decades. It could be that 100 years from now, the Earth's magnetic field will be the other way around. Now, it's probably not going to happen in 100 years. We're probably not in that process of it happening right now, but we are about 500,000 years overdue. It happens every 250,000 years on average, and it hasn't happened for 750,000 years. So it might be happening, especially considering the fact that the Earth's magnetic field has decreased in strength. There's some thought that maybe it's decreasing in strength to the point where it reaches zero and then reverses in increases in strength, Cody, the other way around. This is not reason for panic. Okay, it's not catastrophic. There would be implications, some pretty important implications if that actually did happen or was happening right now, but it doesn't mean we're all going to all of a sudden die. We'll learn some of those implications a little bit later on in the unit when we learn about interaction between charged particles in magnetic fields. Let's take a look at the average magnetic field of a bar magnet. Clearly, bar magnets are going to vary in strength, but on average, they might be about 10 to the minus 2 Tesla, so about 1,000 times the strength of the Earth's magnetic field. Now, you guys just did an activity with bar magnets. When you brought a compass nearby the bar magnet clearly affected the compass more than the Earth's magnetic field. Why? Because the bar magnet's stronger. Even with the weak bar magnets that you used, it was still stronger magnetic field than the Earth's magnetic field. On average, about 1,000 times stronger. Sunspots, which is kind of weather that takes place on the sun, releases charged particles, has about a strength of 10 times what the average bar magnet has. So about 10 to the minus 1 Tesla. Anybody ever had an MRI? Nobody's had an MRI? Yes? Yeah? I had an MRI in my knee once, and I was shocked by the questions they ask you before you get this MRI. They make you fill out this big form, and some of the questions are like, have you ever had metal embedded in your eye? Like, what? Well, if it's ferromagnetic material, ferromagnetic metal that you've ever had embedded in your eye, and you're going to use magnetic field strength of 15 Tesla on your head, then that might be a big deal. Now, I don't know what happens if you answer yes. I don't know what happens if you say, yes, I have had metal in my eye. I don't know what they do then. Okay? But if it's a ferromagnetic metal that's in your eye and you expose your eye to 15 Tesla, that might be a big deal. Okay? The strongest human-made magnet, about 40 Tesla, so in the order of magnitude of 10 to the 1, just as an MRI machine is, but about 3 times the strength of an MRI machine. Now, this is what you do not want to get close to. Okay, the next one, a magnetic neutron star, which has a magnetic field strength on average, I suppose, of about 10 to the 11 Tesla, which is 10 to the 10 times stronger than the strongest human-made magnet ever made. Like, this is probably so strong that it would literally suck the iron out of your blood. The good news is, if you ever started approaching a neutron star, magnetic neutron star, you'd be dead long before you ever had to worry about the iron being sucked out of your blood. So don't worry about that. Okay, don't worry about that one. You don't need to memorize these numbers, but you can imagine how later on in the unit, when we do calculations with magnetic fields, you can kind of keep rough numbers in the back of your mind to know if answers are reasonable. Okay, you calculate the magnetic field caused by a bar magnet to be 10 to the minus 27. Well, you're wrong, right? You know that it should be, you might not remember that it's on average 10 to the minus 1, but you know it's not 10 to the minus 27, right? If you calculate, you got one of those questions that has a page of information, and it's this time involving an MRI machine, and you calculate the magnetic field to be 1,228 Tesla. Well, you're wrong, because an MRI should have a magnetic field somewhere in the range of 10 to the 1-ish Tesla. So again, don't memorize those numbers, but know at least if something is reasonable or not reasonable based on these. I'm going to draw you a picture here, and then I'm going to flip the slide to the last slide here. And I'm going to blow your mind with something I'm going to teach you. That's the next slide. It's related to this one, though. It's a picture of the Earth. Now, the Earth has this giant bar magnet inside it, of course, as we all know, right? It doesn't really have a bar magnet inside it, right? It has a magnetic field that's caused by molten magma churning around within the Earth, somehow generating this magnetic field that looks like the magnetic field that surrounds a bar magnet. It's not really. It just looks like the magnetic field that surrounds a bar magnet. This is the equator right here. If I was to stand at the equator right there with a compass, which way is that compass needle going to point? Keep in mind, this is Canada up here, and this is the Antarctic down here. Yeah. It's going to point south? So you mean it's going to point, which way is it going to point? Down this way? Okay, yeah. You think it's going to point north towards Canada? If you were to take a compass in this room right now, it would point this way towards Calgary, right? Because Calgary is north of us. But wait a second, we defined the direction of the magnetic field as being the direction that a compass needle points, but also away from the north and toward the south. So shouldn't it point toward the south? Yeah, it does. Yeah, that's the confusing thing about this, although that's not the thing that's going to blow your mind. This is actually magnetically south, and this is magnetically north. Now, geographically, we still call this north, right? And when we navigate, we still call it north. But it's not magnetically north. It's magnetically south. Now, in a couple 100,000 years, maybe it's reversed, and maybe it actually is north. But right now, it's magnetically south. If you're lost in the woods and you're trying to get out with a compass, don't change anything. Whatever you learn in Boy Scouts or Girl Scouts, don't change anything. Because as long as when we navigate, we use the same system as everybody else uses when they navigate, which is calling this north and this south, it's all good. It doesn't matter if it's not really called north, as long as everybody calls it north. Look, we could call this Bob if we wanted. Where are you headed? 37 degrees west of Bob. Well, as long as everybody has the same understanding as to what Bob is, it doesn't really matter what we call that, right? Okay, if everybody's calling it north when we're navigating, that's fine, even though it's not really right. Okay? Don't change anything in your day-to-day lives. Just understand that when we call this magnetic north, it's not really magnetic north. It's really magnetic south. Geographically, we call it north. Magnetically, we would technically call it south. So, when you were 5 years old, and you wrote that letter to Santa asking for that big Lego, that big Star Wars Lego set, and you didn't get it, you have to understand why. When you write that letter to Santa, right, you write it to Santa Claus. What's his address? Do you remember? Yeah, North Pole. North Pole. Postal code. You guys remember this? HOHOHO, yeah? You guys don't remember that? When you wrote that letter to Santa and addressed it like this, there was a problem. It probably never got delivered by Canada Post because Canada Post recognized that Santa Claus doesn't live in the North Pole. He lives in the South Pole, magnetic South Pole. And the penguins, which we think of living in the South Pole, they really live in magnetic North Pole.